So welcome to the second lecture. I'm trying here to complement the book sort of by talking about things that are not the focus of that book, because I think the book does a very good job at talking about these things. So hopefully I can give you a few different angles of the topics of this course. So therefore it's going to take a little while before we get to writing some actual cock in this lecture today. So we're talking about something called the Curry-Howard correspondence, and I will get to what that is. So let's think for a second about inductive definitions. I'm not talking about the when you write inductive in cock, although in a sense I am. But I'm thinking just when you're defining, for example, a grammar. Here's the grammar of propositional logic, not the complete propositional logic, but it has true and false, conjunction and disjunction. So this grammar, it tells us how formulae for propositional logic may look. It gives an inductive definition of the syntax. And what does this mean? Well, that means that if you have a formula phi, then it must have one of these four forms above. It's either true, it's false, it's a conjunction, or it's a disjunction. It cannot be anything else. And what that gives us is that it allows case analysis, right? If we have a phi, then we can reason about, okay, what if it's true? What if it's false? What if it's a conjunction or a disjunction? Furthermore, this structure is implicitly finite. If you think about it, this looks like we can just put like true and 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 true. But whenever we write a specification like this, like we are implicitly thinking of finite structures. And what that gives us is that it allows us to do induction proofs. I'm going to try to motivate sort of why that works, sort of how induction works for these kinds of structures. So when we write a grammar like this, in some sense, what we're actually defining is the following thing. So we're saying that here we have phi 0, which has true and false in it. We're also defining phi 1, which are all the conjunctions and disjunctions where the operands come from phi 0, come from the previous set that we defined. This set also includes the previous set. We can build a hierarchy like this up to some arbitrary phi omega, where it's the conjunctions and disjunctions, where the operands are from the previous level, so to speak, and it includes all previous levels by this final term here. So if you have, sorry, this should be a phi. If you have phi n, then that's the set of formula with a maximum of n connectives, where connective is one of these things. So phi 0 has 0 connectives, phi 1 has at most 1 connective, because a and b here come from phi 0, which have no connectives. Okay, so this means that whenever we what we're saying when we say, okay, we have a term that follows this grammar, what we're saying is there is some level in this hierarchy that's enough, like it's big enough to cover the thing that we have. And the important thing that this gives us is that it gives us an induction principle. We can prove things by induction. So if we have some property P over formulae phi, where phi comes from some level, whatever level that is, we can prove 3 things in order to prove that it holds for any phi, by proving that it holds for any formula from the from phi 0, basically it holds for true, it holds for false. We can show that it holds for P of A and B, assuming that PA holds and PB holds for some level K, for an arbitrary level K, and the same thing for conjunctions. And the reasoning here is that, okay, so we show that it holds for true and false. And that means that if we assume that it holds for everything that's in phi 0, and we can show that it then holds for A and B and A or B, then we've proven that it holds for everything in phi 1. But since we're doing this for an arbitrary K, we can move up from phi 1, we can prove phi 2, from phi 2 we can prove phi 3, and so on, up until whatever level we need. I'm hoping that this makes sense. Feel free to shout in the chat otherwise. And I said that we were thinking about this in terms of like math definitions, not Coq definitions. But let's compare it to algebraic data types of your favorite programming language. By now, I'm assuming that your favorite programming language is Coq. That's why I've written that first. But it could just as well be OCaml or Haskell. And I think those are the allowed favorite languages that you can have. So when we write a data type definition like this, it also gives us an inductive definition, or in this case, it's the shape of list, right? It's the shape of lists of natural numbers even. It means that we can have, if we have a value of type natlist, then it must have one of the two forms above. So we can do pattern matching, which we do a lot in functional programming. And because any value of this type is finite, except possibly in Haskell, it allows you to write recursive functions that terminate. Depending on the language, it might terminate or not. In Coq, you know, it always terminates. But you see here that the comparing this to what we had here, sort of, we're doing the same sort of thing. We're saying what does the smallest list look like, and how do we build the next level of list, or whatever structure we're defining. Now, slightly more interestingly, let's say we want to define some kind of inductive relations over these formula that we defined. For example, we can say, when is a formula true? Well, A and B is true if A is true and B is true. A or B is true if A is true or if B is true. And the true constant T here is always true, right? If you think about it, so these are sort of, this is a relation, this shows when it holds. But the relation that we see here, it gives an inductive definition of the derivation trees of this relation. What do I mean by that? Well, I mean exactly the same thing as before. If you have a proof of phi true, then that proof must have one of these four forms above. So that allows us to do case analysis. We know that if this is true, then it must be the case that it's a tree that has the root A and B true, or A or B true, one of these two, or T true. It must be one of these four cases. Typically, we also require derivation trees to be finite, which again allows proof by induction. So let's do the same exercise that we did before. I would claim that when we're writing these rules like this, what we're actually defining is a hierarchy where, let's call the trees tau, where we have tau 0 being the containing only this tree, that is just the root T true and no children. We have the set tau 1, which is the set of all trees where the root is a conjunction or a disjunction, and the immediate children come from the previous level. So basically, this is where A true and B true must be T true because it comes from the previous level, and the same thing for here. And we can keep building until we get this. We get an arbitrary depth in our hierarchy where we always have the previous, the immediate children of the root come from the previous level of the hierarchy. And this, so if we want to give some sort of intuition for what this index means here, I would say that tau n is the set of derivation trees for formulas in phi n. So phi 0 that contained true and false, and the only one of those that are true is true. So that thing is in tau 0 and so on. But so sort of this, we can use using the same motivation. This gives us an induction principle. So if we have a proof obligation, which is phi true implies p of phi for some phi, and for a phi true that is in one of these levels of the hierarchy, we can prove this by proving the base case that where we should prove p of t because the phi true argument came from tau 0. And we have the three other cases. Either phi was built from this derivation rule, and then we can assume, just as before, we can assume that A is true, B is true. We can assume that P of A is true and P of B is true. And then we have the other two rules here. Again, we are now saying, okay, so we prove it for tau 0, and then in these three cases, we are assuming that the immediate children in the derivation tree that we got here, they're coming from the previous level. So if we can show that it holds for trees in tau 0, then by these three, we can show that it holds for all the trees in tau 1. And again, moving on, we can show that it holds for anything in tau 2, tau 3, tau 4, tau, and so on, up until the whatever n you need. So I think this is probably things that you've heard about before. If you've read the TAPL, this is the sort of in the introduction chapter, more or less on sort of how to motivate that we can do structural recursion like this. But it's important for what's to come, because we're sort of used to thinking, maybe we as computer scientists aren't, but when we talk about logic, a lot of the time, what we're thinking of is sort of reasoning logically, but in abstract, some sort of abstract sense of convincing yourself that something is true. Whereas what I'm showing you now is a very syntactic means of proving things, rather than thinking abstractly in terms of everyone who is from this Greek island are liars, and this person is saying that they're from this Greek island, therefore I can't remember the details. We're actually thinking about it in terms of building these trees. So I would say that this is a syntactic way of thinking about proofs. So rather than saying that proving that something is true is about sort of convincing yourself that this is true, I would say that proving, for example, that if we have some formula phi and want to show that that's true, then what we need to do is produce a derivation tree that has phi true as its root. For example, let's say we wanted to prove that t and false or true is true. Then rather than reasoning about it, we just syntactically say, okay, what can we match? Well, the root has to be one of these, and then we have to be able to show the left and right operand, and this turns out to be a conjunction, so it has to be this one or this one, and then we can build this tree here. So it's a very syntactic way of thinking about proofs. And what's even more interesting is that when we think about these induction principles that we talked about, I would say that rather than them just being trees, they're actually defining procedures for how to build this derivation tree. There's a question in the chat. To formally motivate these set theoretic induction principles, I suppose we need to appeal to some axiomatic principle of induction for example, natural numbers. Yes, exactly. That's a very good point. So basically, all of these arguments come down to some properties of sets, and then it's induction on natural numbers all the way down. So we basically reduce it to an argument about induction on natural numbers. I agree. That's a very, very, very good point. So induction principles, they are procedures for building derivation trees, I would say. So let's take an example. Let's say that we define another relation. We call it megatrue, and a formula is megatrue if basically all the leaves are true, is what this is going to come down to. So A and B is megatrue if A and B is megatrue. A or B is megatrue if A and B is megatrue. And then we want to show that phi megatrue implies that phi is also true in the old sense here. If we were to do this by hand, we would probably say we do this by induction over the derivation tree of phi megatrue. We have the base case. In the base case, the megatrue came from using this rule, and then phi is t, and we know that t is true trivially. In the second case, we have that phi megatrue came from using this rule, and then by the induction hypothesis, we get that A is true and B is true, and that's exactly what we need in order to show A and B is true. And then the third step, where we have used this rule, it's similar to this step, but we can use either rule for A or B being true. So how is this a procedure? Well, in a sense, it's a bit abstracted because we have these sort of proof obligations given by our induction procedure. But if we look at, okay, so we don't have the derivation, no, the induction procedure for, or induction principle for megatrue, but we have it for here. We're saying that I argued here that if we can show these four things, for megatrue, it will be three things because there are three rules, right? If we can show these things, then here's how you build a derivation tree of it. We can, if we want to, be even more direct in this particular proof and say, okay, if we're doing syntactic proofs, then what we're saying is that I have a proof of phi megatrue. I need to produce a proof of phi true. Basically, I have one derivation tree. I need to produce another derivation tree, which happens to be of the same over the same formula. I might start writing it like this. Let's call the trees of megatrue sigma, just to see that they're different. So we have some sigma. It's of type phi megatrue. It's a derivation tree of phi megatrue, and we want to produce phi true. I'm just using some kind of functional-like language, but it's meant to be a function over the derivation trees. So how do we go about doing this? Well, we've said that when we write these rules, we're actually defining in inductive structure. We know that it has to be one of these three cases, so we can do pattern matching. So we'll say, let's match on this derivation tree of phi megatrue. If it's the case that this derivation tree was p megatrue, then phi must be t. So how do we build a derivation tree for t being true? Well, we just use this rule here. So it's simple. Let's say that we have this shape. So this is some subtree of the derivation tree A mega true and B mega true, and the root of it is A and B is mega true. That means that phi had the type, had the shape A and B, meaning we need to produce this derivation tree. How do we produce this derivation tree? Well, this rule says that we need to provide a derivation tree for A is true and a derivation tree for B is true. So how do we get there? Think about that for a minute. Please write it in the chat if you have an idea. So we have a derivation tree for A mega true. We have a derivation tree for B mega true. But how do we get a derivation tree for A true and B true, which we need in order to build this thing? I'll give you a minute to just think about this. Think about this in terms of just, don't think about it in terms of proofs. Think about it in terms of just programming. How can we get something that has the type A is true? So we have a suggestion here: recursive calls to build proof. Exactly. We know that we have a function, we're defining this function, which takes a proof of phi mega true and produces a proof that phi is true. So, and we, from this pattern matching, we saw that we have a subtree that shows A mega true. So if we feed that back to the function, then the type of this function, so to say, is it takes a phi mega true, it gives us a phi true. So if we give it A mega true, it should give us an A true. And that's exactly what we need in order to build these things. And the same thing for B mega true. The final case then, the disjunction, it's the same thing there, right? We have a subtree of A for A mega true, we have a subtree of B mega true. We can use either of them. Let's choose A mega true, and then we call the build proof function recursively. So as long as this function terminates, I would argue that we've shown how to take a proof that is a derivation tree of phi mega true and produce a derivation tree that is a proof of phi true. But we've done so rather than using induction or sort of appealing to some sort of reasoning. We've written a program that does this. And this thing, this connection between proofs and logic and programming is called the Curry-Howard correspondence, sometimes the Curry-Howard isomorphism, sometimes the Curry-Howard equivalence. The first instance of this was discovered sometime in the 30s, I believe, by Haskell Curry. And then, because this was before the internet, if you will believe such a thing, this was just sort of these observation. This observation was just circulated privately between different people. Among them, so we have Haskell Curry, and one of the people who are talking about this, who later wrote about it for the first time, it was called O'Camel Howard. No, sorry, he was not. He was called William Howard. So because they are the sort of the two people who talked about it publicly for the first time, it's named after these people. And the important thing, sort of the connection that they're doing here, is that proofs, they behave the same way as programs, and propositions, they behave the same way as types. Just as we saw on the previous slide, we had the type of the argument we're giving here is a proposition, phi is mega true. The proof that we're writing is a program that's working over these structures that have these types. So you can take this further, you can take this quite far actually. So we have propositions being types. So propositions in logic would be types in programming. Proofs in logic would be programs or terms in programming. Implication, if you have A implies B, then that behaves the same way as a function type would. So if you think about it, we have A implies B that says, if you give me proof of A, I will give you a proof of B, or you will get that back. And it's the same way a function works. If you give me a value of type A, remember that types are proposition, I will give you a value of type B. So the values are the proofs, or the terms, and the types are the propositions, or the other way around. And I was saying values here, I was saying terms here. There's another correspondence there between evaluation of terms in programming and simplification of proofs. There can be multiple proofs of the same thing, and sort of simplifying that is going to give you a smaller proof. That's implication. If you have conjunction, I'm writing A and B. I mean that now in the logical sense, not the formula that we defined earlier in the lecture. But if we have a proof of A and a proof of B, well, that behaves as a product type. We have an A and we have a B. This is a tuple of A and B. If we have a disjunction, we have an A or we have a B that behaves like a sum type, like in your algebraic data type, where you say it's either one of these or it's one of these. So they behave the same way. If you do case analysis in logic, that behaves as pattern matching, just as we saw in our proof procedure that we wrote for mega true implies true. The concept of true is the unit type. The concept of false is the empty type. And I think this becomes very clear once you start thinking about proofs in this very syntactic manner. So let's say that we're reading some logic text, and it says lemma 1 is for all n is smaller than n plus 1. We can put on our Curry-Howard glasses, and we can read this as, given any n, lemma 1 can produce a proof of n is smaller than n plus 1. Or if we think of it even more from a functional perspective, lemma 1 is a function that takes numbers n and produces proofs that this number n is strictly smaller than n plus 1. Take another example. Here we have lemma 2 that's saying for all m and n, if m is smaller than n, then m is smaller than n plus 1. So we can put on our Curry-Howard glasses and see this as a function. Lemma 2 is a function from a proof of m is smaller than n to a proof of m is smaller than n plus 1, right? So if we are then tasked with proving that x is smaller than x plus 2, either for all x or for some particular x, we might say something like this. Using lemma 1 with x, we get x is smaller than x plus 1. Let's call that fact 1. And by using lemma 2 with fact 1, so we know that x is smaller than x plus 1. We use lemma 2, then it must be the case that x is smaller than x plus 1 plus 1. And by some properties of plus, we get that x plus 1 is x plus 2, and then we've proven the thing that we needed to prove. And in a sense, what we're doing, although we're writing this with natural language, one way to think of it is basically programming, right? We say, okay, let's call the function lemma 1 with x and get fact 1, that x is smaller than x plus 1. we're giving it x. And then let's call it fact2. We call lemma2 with x and x plus 1, and it also wants the proof that the one is smaller than the other. And then we get fact2, and then we simplify fact2, and then we're done. In a sense, this is similar to, I don't know if you've ever been in an unfamiliar code base. Let's assume that this is thousands or tens of thousands of lines of code, and you're writing this verify operation thing. You have an operation as an argument. You need to produce a certificate of a log entry, and you might go to think, okay, let's just look at the functions here. So if I had a log entry, then I could call certify log entry, and I could get one of these certificates. How can I get a log entry? Well, there's a function that returns a log entry, so maybe I can write the whole thing like this. In a way that you're sort of looking at how can I connect the things, the types in the functions that I have available to me in order to get the type that I want. We're doing exactly the same thing with our proofs here in the previous section here. So it's very much they're very much connected. Let's think about true and false. The proposition true, that's basically, well, it's true. That corresponds to the unit type being the type that has a single constructor, usually written like this, also called unit, and it carries no information. And just as true is always true, we can always produce a proof of true. Just as we can, whenever we don't need to provide anything, we can always just write parentheses, parentheses, and we get this value of type true. Whereas false is never true. So there should never be a proof of false. If there's a proof of false, then we've done something wrong. So the proposition false corresponds to the empty type. So the empty type, that's the type that has no constructors at all. That means that we can never produce a proof of false. So let's sort of, usually we've been taught that if you have false, then you can prove anything. And the sort of programmatic equivalent of that is writing a proof procedure like this. So this is ex falso quodlibet. That, I think it means from false follows anything. If you have a proof of false, you can prove anything. Just replace anything with your favorite thing that you'd like to be true. How do we do this? Okay, let's start by pattern matching over P. And as soon as we've pattern matched on it, we've now written all the possible cases, all the possible ways that we could have gotten a P, which are 0, because we can never build this. So we can't have this value. So it's enough to pattern match on it. And now we can say, look, for all the possible cases for all the possible shapes that P could have had, we've produced a proof. Just happens to be the case that there are 0 cases for this particular value. So this thing, I'm not a logician, and this is not a course in logic. So this goes deeper than just saying, oh, these two things are kind of similar. If you write the rules down, you can see that the rules look exactly the same. There's this famous paper, I think, by what's his name? I can only think of Curry and Howard. No, Phil Wadler. Phil Wadler, I think, did this paper where some things are written in blue and some things are written in pink. And if you put on blue goggles so that the blue text disappears, then you have logic. And if you put on red glasses or the pink glasses so that the pink disappears, then you have basically the lambda calculus. So you can show that the rules actually coincide. And there are a bunch of other connections now. We've just shown a little bit of them. In terms of one of them you probably know, system F being equivalent to the polymorphic lambda calculus. Turns out that some flavor of modal logic corresponds to monads, thing that some functional programmers use to reason about things like state and side effects and other things as well. Linear logic has an equivalence in session types, turns out, and many, many more. So there is a recorded talk by Phil Wadler. He also wrote an article in the Communications of the ATM called Propositions as Types, which is sort of a lightweight introduction to these things. So I would recommend you to watch this talk if you'd like to know a little bit more about what the Curry-Howard isomorphism is about, without necessarily taking a whole other course on the topic. So I told you in the first lecture that typically we use tactics when we write proofs in Coq, but what we're actually producing are these dependently typed proof objects. And these proof objects, they reify, my favorite words, the Curry-Howard correspondence. In the sense that inductive definitions, they are inductive data types. They don't have the same shape. You write inductive definitions by writing inductive data types. When you're doing proofs, you are explicitly building proof objects in this very syntactic manner that I showed you before. If you do case analysis in your proof, if you use destruct, for example, then that turns into pattern matching in the proof object, just as we did before. If you have a proof object that is an implication A to B, then that is actually a function. The proof object itself is a function from a proof object of type B to a proof object of type A to a proof object of type B. And what the function does is that given this proof object A, it pattern matches and calls other functions and everything it needs to do in order to build the proof object B. And then induction shows up either directly or indirectly as recursive functions. And in Coq, because we have this totality requirement that all recursive functions must terminate, the recursive functions that we write are guarded in the sense that the thing that we are using to define the variant must use structurally smaller terms. And they must appear in guarded positions. So let's go, as an Italian plumber I know would say. Let's start writing these things and think about what they are. I've just written the same definitions we had from before. We could say inductive phi is either true or false, or it's and with phi 1, phi 2 being phi. Maybe we should call them A and B so that we're not confusing type name and the variable names. And or is the same thing, A and B to phi. Should write this in the right way? Yes. So this is just a regular inductive data type, nothing strange with this. Let's write this relation here. It's also a inductive data type. Let's call it is true. And this is now a property of formula. So it's going to take a phi and it's going to produce property like this. And we have 4 cases when we're building this derivation trees. We have the axiom, which is when that is true holds for t. We have the AND case where for all A and B, if A is true and B is true, then and AB is true. We have the two OR cases where we're saying for all A and B, and if, let's write them out first. If A is true, then so is OR AB, and then the next one is just going to flip this A to B. To be consistent here. Right, so what is this then? This is just this constructor. It just takes, it actually takes four things. It takes an A, it takes a B, it takes a proof of that A is true. Basically, it takes the derivation tree that shows that A is true with this definition. Does the same thing for B, and then the type of this thing is that A and B is true. It means that the proposition that this value represents is that A and B is true. Let's do the same thing for mega true. Mega true, that's also a property over phi. We have mega true axiom. Should probably call this is mega true. So T is mega true. Just going to copy this thing. Is mega true. I just want to show off my multiple cursors. Like this, right? So again, this now defines this derivation tree, which is our proof object. Let's get rid of these things. So we had this thing we wanted to prove. We had a theorem called mega true is true, which said for all formula F, we have that if is mega true F, and that implies is true of F. Go ahead and prove this. We introduce F and this hypothesis that F is mega true. We can do induction over F, perhaps. We get four cases. This is true because of the axiom. This cannot be true because, or well, this whole thing is true because is mega true of F does not hold. We can do inversion of HM as well to see that both F1 and F2 must be mega true. We'll do substitution as well. And now we have what we need. The induction hypothesis says that if F1 is mega true, then F1 is true as well. So we will apply IHF1 in, or maybe we'll just do apply T and get two subgoals. Apply IHF1, and now it's true by assumption. This thing is going to be the same. We want to show that F2 is true. We can get that if we have is mega true F2, and we do have that. So, oops. So we'll do that. And then this one, probably the same. Apply T for 1, for example. You can apply IHF1, and this is true by assumption. So we've proven this like this. But we can just as well write this as just a regular proof object immediately. So let's call it mega true is true prime. That takes f, which is a phi, and a proof that h is that f is mega true f. Notice here that all of this that we're doing is possible because we have dependent types, right? Is mega true, like the shape of this depends on the value of this thing. So the shape of this value depends on the shape of this value, and so and this is captured in this dependent type. We want to produce a is true of f. So other languages, as we will see when we get to the Agda lecture, other languages with dependent types have better support for this. But what we can do at least is to write these holes as underscores. And here we can say, oh, I cannot infer this placeholder of type is true f. So I'm trying to produce something. I need to produce something of type is true f. So let's see how we did this thing in when we did it by hand. We wrote, I think I managed to crash Keynote. Nope, here we are. We actually did pattern matching over the proof of mega true. So let's do this as well here. Let's do match HM with end. And what are the cases that we can have? It's one of these three cases. So either it's empty axiom, and it's something, or it's empty and then it's something, or it's empty and it's something. And at least I think it's quite difficult to get like the right number of parameters right. So we're going to let the type checker guide us here. The constructor empty and in type is mega true is expected to be applied to 4 arguments, while it's currently applied to no arguments. That's true because it takes an A and a B and a proof of A being mega true and B being mega true. So let's write A, B, proof of A being mega true and a proof of B being mega true. So let's stop complaining here, and then this is the same thing, 4 arguments. So AB, HMA, HMB. So now it's happy with the pattern matching. Now it says, okay, I need to produce an is true of T here. So the type checker has managed to figure out that this F must have the shape T, because this is the only way that this thing can happen. So the type checker is doing some of this reasoning for us with what shape things can have due to dependent pattern matching. So we need to produce a proof of is true T. That's simple. We have this constructor called T axiom. So again, we don't have to think about this in terms of proofs. We can just say, we need to produce something that has this type is true T. We have a constructor that has the type is true T. So we can just write that, T axiom. Here we can't infer this placeholder. It has to have the type is true A and AB. We have a constructor that has this type as long as it's given these other 4 things. A, B is true A is true B. Let's write that. T and takes an A, takes a B. It takes, let's just fill this up with holes. So it cannot infer this placeholder. It should have the type is true A. So how do we get the type is true A? See what we did. Well, we called this function recursively, right? Called build proof A mega true. So let's call mega true is true prime. We're calling the function recursively. It takes some phi. The thing we want to take, because in the end we want to produce is true A. So this f parameter should be A. the argument should be A. Then it takes the proof that A is mega true. We have that in HMA. Let's see if we can even get that from the. We get a little bit of help here. It says that so this has to be is mega true A. In the environment we have these things, and we can see HMA actually has the type is mega true A. So this sort of being able to be interactive with the type checker helps a lot when you're doing these things, right? Is mega true. No, sorry, we called it HMA. So it seems happy with that. Now it needs a proof of is true of B. So let's do exactly the same thing here, but we'll replace the B by an A by the B. Now it seems happy with this branch. So let's do this thing. We need a proof of is true or AB. We have a constructor for that called T or 1 or T or 2. We could use either of them as we saw. Let's do T or 2. T or 2 takes an A and a B and a proof that B is true. Take an A and a B, a proof that B is true. It's going to be a recursive call HMB just as before. And now we're done. We've written this thing. This thing is now a proof, just as the thing we wrote here is a proof. And actually, what we can do is we can print mega true is true. So this is now I'm printing the proof object that we built here. And as you can see, it's quite simple, but it's generated here. Just simple 119 lines of code. But that doesn't matter. We don't have to be concerned with this complexity. This is actually, we can see it's sort of doing the same thing. All right, we were doing it slightly differently. We were doing induction of F. Let's see if we can rewrite this to do induction over HM instead. Should be more or less the same. Apply T and this is just an assumption. This is just an assumption. Let's do it exactly the same way, so like that and like that. So now let's print it again. Okay, this is a bit nicer, but you can see what it's doing. It's calling this thing called is mega true ind. That's the induction principle of is mega true. We'll get to induction principles in just a second, but it's now built a proof object that's more or less the same size as ours. The difference is that this one is using the induction principle as sort of a helper function, whereas the function that we wrote here is not based on induction. Instead, it's sort of, well, in a sense, it is built on induction. It just isn't using the induction principle. So I just said that tactics build proof objects, and proof objects are programs. So can we use tactics to build programs? If we're using tactics to build proof objects and proof objects are programs, it sounds like we can actually write functions using tactics. We can definitely do that because they are the same thing. So let's write a function that counts all the occurrences of false in a formula. Let's call it count false. It takes a formula which is type phi and it produces a nat. Now instead of writing colon equals, I'm just going to write period. This now brings Coq into proof mode. So let's do what we can do is we can say show proof. And now down here we can say this is the current proof state. This is the current proof object that we're building looks like with these holes. So we say that this is now a fixed. This means this is an anonymous function which is recursive, and the name for the internal name for the recursive call is count false, and these are the arguments and their return type. Okay, so let's do destruct f, and let's show the proof again. we've now done destruct F. That has turned into a pattern match, where we can see it's automatically expanded this. So the 4 cases that it can be is T, F, and AB, and or AB. And we have 4 different goals here. You'll notice that this thing is slightly different. You could imagine that this would just say question mark goal 1. Instead, it's a function. It's applying a function to AB. Why it's doing this, I'm not really sure, but we can see that this is going to be the same thing, right? So we have these 4 cases. If we look at what we're trying to prove up here, this doesn't really look like we're used to. We're used to having a prop down here, and now we have a NAT. So we're looking at this goal. What should this natural number be? I would say that if we're looking at true, then there are 0. So I'm just going to say apply 0. So usually when we say apply, that means apply something, apply a theorem or lemma whose conclusion has the same type as this thing. And in a sense, 0, because we're sort of unifying what is proving, what is proofs, what it's programming, 0 is, in a sense, it's a proof of itself, right? So we're applying 0. Let's show the proof again. And now we've seen that in the arm for the true case, we now have 0. In this thing, which is the current goal, as you can see, because it's blue, we can do apply 1. Let's show the proof again. We're now filling in this thing. So how do we count the false when we're in this case? Well, I would say that we do count false. Note that count false is in our context as well as a function from phi to nat. Let's do count false F1. 1 is in our context as well. Plus count false F2. And show the proof. And now it's filled this in. So it doesn't normalize this thing, but you can imagine that you could do that. And this thing is going to be exactly the same thing. So now we can show the proof, and we've built this thing. It sees that in both of these cases, it's going to be, going to do the same thing. So the difference from a proof and a function is that we want to compute with a function. If we just write QED as we would with a proof, and we try to do compute count false of, I think it should be in parentheses, T and FF. No, that. No, sorry, and FF. Then it says that count false. Well, that has the type nat, but it hasn't done any counting, and that's because the QED here it produces an opaque object. It contains something that it doesn't unfold when doing computation, which is usually good because we don't care about the proof object. We just care about the proofs existing. We don't want to unfold them because that might complicate our proof search. So instead, we write defined here, and now we can compute with that. And again, we can print count false. You can see that it's a function that is more or less what we would write ourselves, but maybe we would write it in a slightly different way. We would probably write it like this. I've cheated a little bit in this here, in this way, but I think you would agree that these two things are equivalent. So we can write tactics. We can write functions using tactics as well. So let's remember this when we move to induction principles. There's a question in the break about induction principles. So we said before that we can prove P of phi for any phi if we can prove these 4 things. So again, let's put on our Curry-Howard glasses. We're saying that if we can provide these 4 things, these 4 proofs, or if we can provide proofs of these 4 properties, then we will get a proof that P holds for any phi that we can give it. So we can give this whole thing a type. We can say that the induction principle for phi is going to be a function that takes a P, that's the property. It takes a proof of P of T. It takes a proof of P of F. It takes a proof that for all AB, if PA and PB, then that implies P of A and B. And a proof that for all A and B, PA and PB implies PA or B. And the thing that we get back is a function from any phi to the proof of that phi. So we've now again reified the induction principle into a function. It's a function that takes a property and a phi and shows that it gives a proof of that property holding for phi, assuming that we can give it these arguments. And we can do this by hand, and I think we have plenty of time, so let's go ahead and do that. I'm going to jump up here and so that we can see these things. So we can write a fixed point called phi in prime. It takes, let's see, what was the type here? It takes a P, which is of type phi to prop. It takes call it case T, which is of type P of T. It takes case F, which is of type P of F. It takes this thing, let's call it case and, which is of type for all A, B, if P of A and P of B, let's be consistent with our usage of parentheses, then P of and AB, and it takes case or, doing the same thing as above. And so we can choose how to do this. What we want is for this to be a function for all phi to P of phi. Because I think it's clearer, I'm going to say that it takes an F, which is a phi, and it produces P of F. We could also have said that this takes for all F colon phi, like this. But I think, let's see if this is the case. No, this actually works. But I think it's if we do this, then we have to write this thing as a fixed, like one of these anonymous recursive functions. So I prefer to write it like this instead. So let's see, what does it want us to do? So it wants us to produce a proof of P of F. Well, so I'm not going to scroll back, but we had an idea for how to do this. So we're going to match on F and say that if F is a T, then let's just do this so that we can get just so that we can get some help here. So it needs a proof of P of T. Luckily, this function takes as an argument a P of T called case T. So we just write case T here. Similarly, for the false case, we have case F that has the right type. Let's write out these cases. We have and AB, and we have or AB. Here it needs a proof of P and AB. And it gives us some hints for sort of what's in our environments. We can look here. Here we have something that seems to produce. We have a function that produces a P of and AB, and that's the parameter case and. So let's use case and. It needs an A and a B, it needs a proof of A, it needs a proof of B, and it produces that. So the case and, it takes an A and a B, that's our A and B here, because we want the conclusion to be this thing. And then it takes two more things. This hole here should be P of A. How do we get a P of A? Well, it's the trick that we did before, right? We're writing a function that's producing P of F for any F. So we'll just do a recursive call by int prime with A. And of course that won't work, I realize, because A has type phi, it's expecting to have phi to prop. So we need to give it all of these things. We need to pass all of these things that we have. So we need to pass it P, pass it case T, we have to pass it case F, we have to pass it case and, we have to pass it case or, and then we can pass it an A. And now that this together should give us a proof of P of A. It seems happy. It's pointing us to the next one, and that's going to be the same thing again, but with B instead of A. Seems happy. So this case is going to be exactly the same as this. So I'm just going to go ahead and copy this, and case 4. So now we've written our own induction principle here. Again, you may have noticed this, maybe the book probably says so. When you define a recursive data type, it says phi ind is defined. So if we print phi ind, if you see it, it's sort of in here we have something that looks very much like this, only it's giving bogus names to all the parameters. So F is a proof of PT, F0, that's a proof of PF, F1, and so on. So it's doing, and the whole thing is called capital F. So it's doing exactly the same thing as we wrote here. But that shows you that there's nothing magic about induction. We can just write it, write these fixed points like this. And now let's say let's go down to, we have our phi in prime. Let's write another version of the theorem called mega true is true double prime. It says for all F is mega true F is true F. Oops. Yeah. So we'll intros F and HMT, maybe we called it HM before. If we want to use our own induction principle, we just say induction over F using phi ind prime. And as you can see, the difference between the two is the same because they are equivalent induction principles. But this way we can specify to the induction tactics what it is that we want to prove. And actually, all induction is doing is saying, hey, we have this function whose return type, whose conclusion is P of F. So just apply this function and I will generate subgoals for all the parameters that are needed. Usually it can figure out what P and F is. It also does a little bit of bookkeeping. Let's see if we can get this to work. Apply phi ind prime. So it's generated 4 goals. Here we have apply T axiom as before. Right. So it's what induction does is that it helps out a little bit with like generalizing the right things. It's forgetting some of the things. let's see if we can we apply it immediately, followed by an intros? No, so now it's not remembering anything. It's not connecting the things. Let's try phi ind, maybe intros f phi ind with. Let's tell it that the thing this looks slightly better. Right, so now we have this mega true f. So now it's doing the same thing as induction would, but it isn't introducing all of these things that induction does for us. It's still keeping the old f around in the context, even though it's that's not there when we do induction. Let's see if we can just do the same trick as before, using t axiom t and t or 1 t. Oh, and like that. No, okay, we only got one of them. Another trick, if you haven't seen it, which is quite nice, you can write proof with, and then a tactic. For example, this thing, auto using blah blah blah, and now we can write dot dot dot, and that means and for all the goals try to do this thing. Let's do intros as well, because we want that. Here we can do inversion of h. Here we can do probably, oops. All right, it's producing worse names as well. So induction helps us a little bit more in that sense as well. We can do inversion of h1, I mean, and some substitution. And now we can maybe we can actually solve it automatically from there. Yes. So I'm skipping these parts of the truth of the proofs because I think that you can do them yourself. The point here is that we've now proven this using our own induction principle. Of course, we could also write this thing as just a definition. Call it mega true is true triple prime, which takes an f, which is a phi, and hm, which is a proof of is mega true f, and it produces is true of f. Let's try to write this by hand. So we'll match. No, we don't even have to match. I was saying, so we should be able to solve this by just calling phi ind, because what we need here. It's now very confused about the unresolved implicit arguments. Let's hope that this doesn't. I haven't done anything stupid. See if we can just do phi ind. Let's do prime. Let's do our own. It takes a bunch of things. Just give it the right number of arguments, so that it can start pointing to. Talking about implicit arguments. I wonder if this is because I wrote the definition. I'm not sure why it isn't pointing to the holes in that nice way that it was doing before. So let's just look at what phi int prime is taking. So it's taking property and the case of true and false and or. So we'll do. The first thing is a property that is true f. No, sorry, is true, of course. So I'm not really sure why it's complaining about these things. Maybe you'll just trust me that we can write this thing instead of watching me get stuck here. You can write this thing. Maybe actually give me a sec. Maybe I actually have it on a different file. Give me a second. Right, that's how I did it. Okay. So I wrote, instead of writing the induction principle for phi, I wrote the induction principle for mega true, and then I wrote it like that. But let's look at the is true. At least this is a proof that you can write this function. I just don't want to waste more time trying to write it by hand now. Which again, going back to the question about which one should you prefer? Should you prefer writing proofs using tactics or proofs using functions? In Coq, you will get stuck with error messages that are very hard to understand if you try to write it by hand. So it's another reason to write them as theorems and using tactics. Sorry about not finishing this. Blah blah blah. Oh no, stuck in animation. Do you know, there's a question, do you know if the core system of Coq, calculus of inductive constructions, has primitive pattern matching or only induction principles or the other way around? I don't know, but I would believe that it has primitive pattern matching, that is sort of dependent pattern matching, because, and then it's generating these induction principles rather than the other way around. That's what I think, but I'm not sure. So the final thing now is that sometimes when we're programming and we write data types like this, especially when we use nested data types or mutually recursive data types, the generated induction principle is not very useful. So for example, here I've written a rows tree. So a rows tree is a tree where every node contains a list of rows trees. So a leaf has an empty list and a single element, and any other thing has an internal node has a non-empty list. And the generated induction principle looks like this. And if we try to read this out loud, what it says is, so for any type and a rows tree or a property that takes a rows tree of that type to a prop, if you can show that P holds for an arbitrary node, then it holds for a tree, for any tree. And this is not useful at all, right? Because every tree is a single node. So what it's saying is, if you can show that it holds for any tree, then it holds for any tree. So the generated induction principle is not sort of recursing through the list, as it were. So a more useful principle would be something like this, where you say that if any tree that is in TS, if P holds for all the trees in the list TS, if you can use that to show that it holds for a node that contains these trees as subtrees, then you have the final thing. And this is where this thing of generating functions using tactics becomes very nice. So let me just show you. This is what it looks like. I won't try to do this live. I've already failed once. This is what the custom induction principle that you could write, and it would be useful. It would look like this. So it's pattern matching on T. It's using the case node that has the expected type, capital for all, that's for all elements in a list. It's calling the induction principle of the list and providing that with a bunch of these things. This took me a long while to get right. Let's see if we can do this in a better way. I'll just copy the definition of a rows tree. And then let's write. So as you can see, if we print rows tree ind, then it says if for all element children p of node element children holds, then it holds for any rows tree. So that's not very useful. So what we'd like is one that says rows tree ind, and there's some boilerplate because we have a type. We have a proposition from rows tree of A to prop. We need this case node that has the more useful type for all E and TS, assuming that PTS holds, then P of node A TS holds. Then you can take any T, which is a rows tree of A, and show that P of T holds. So we could try to write this by hand. Capital T. Oh, right. We need to require import list. Right. So now we can try to write this thing by hand. So this is probably going to be sorry, not by hand, by using tactics, of course. So let's destruct P. Note here that we have, because we're writing a fixed point, we have the induction principle here already. So let's destruct that. I'm probably going to want to have a proof with auto. Let's destruct that. And what is it that I want? I probably want to apply this thing, right? So that I can show that I can generate this proof, because then I get that proof. So let's apply case node. And now we have something like this. No, sorry, something like, wondering what's happening. Now we need to show for all P of children. But we also have this, because we're writing a fixed point, we have a way of generating P of T's. So we want to generate P of T for everything that's in the children. So rather than this monstrosity that we wrote here, we can just write induction children. Just a regular inductive proof. I'm going to write ... because it's a simple subproof. Here it doesn't really matter if sort of you have to know the standard library, but here you can say apply for all cons. Let's do it here. We can solve this. Let's be this here. How do we solve P of A? Well, we have this way of generating P of A for anything, right? We can just apply rows tree ind, and this is just an assumption, because this is exactly case node that we needed. So this can probably find this. Yeah. And here, this is also just the induction hypothesis here. So let's write ... here as well. QED. Oops. All right. Need to call it rows tree ind. Oh, rows 3 int prime. Sorry. Yes. Right. Sorry. What I should have shown you first is why this induction hypothesis, also induction principle that is generated by Coq, why that doesn't help us. So let's write a function called rebuild. It takes a type and a rows tree of A. It matches on the tree, and it has to be a node. Don't care about that thing, and it has children, and then it just produces exactly this. Maybe we do care. It produces exactly the same thing, but we map rebuild of A over the children. So this function does nothing. Why are we expecting? Oh, and an element, of course. This function should do nothing. So we would like to be able to prove the theorem that rebuild is the identity function. So for any tree we have that rebuild of, sorry, A and T, rebuild A T is equal to T. So we'll try to introduce these things, and then we'll do induction over T. And as you see, there's nothing useful in our context right now. There's no induction hypothesis. We have a type, we have an element, we have children, and we need to show this thing, and we don't know anything about anything really. So we just abort this thing. And instead, now that we have this induction hypothesis, induction principle, let's try again to do theorem. I'll just copy this. And we can do intros A and T, do induction T using rows tree ind prime. And now we know that we now have an induction hypothesis that says that for every subtree, it's the case that rows tree of A is equal to this thing. So now we have something that we can work with here. I'm guessing that this is going to be an induction over TS. Why don't we do with auto and see if we can just get rid of this thing. Simplify F equal. And now right, before we do that, we probably want to do something with this version H and subst. Right, so now we know that rebuild A of A is equal to A, and we know that it holds for the rest of the, or the induction hypothesis says that it holds for the rest of the list. No, this says it holds for the rest of the list, and that will give us what we need there. So we can do simple, we can do rewrite H2, we can do rewrite IHTS. No. Let's see what is it that we want. Maybe we do want an F equal here. This is what we want. Let's apply H3 in IHTS. This exactly this. Oh, it's the other way around. Yes. We need simple in H3 and inversion in H3. And now we have the thing that we want. Rewrite IH1. For some reason, rewrite H1 again. And now we're done. Nice. Let's improve this. Sorry for rushing through the proof, but the important thing again is that we now have because we have written our own induction, our own more powerful induction principle, we can do this. An interesting thing that I didn't know before, and that I don't think they bring up in software foundations, is that we could also write this proof as a fixed point directly. I'll show you what I mean. Can you swap there's a question from the chat. Can you swap the auto-generated induction principle for the manually written one so you don't need to write using? Not that I'm aware of. I haven't seen that done, so I think you need to write using. But I'm not sure. I mean, it would be nice. So an interesting thing here. Let's write it this. Instead of theorem, I'm writing fixed point. Colon there. Oh, we found a bug that we should report. List.last. Why is that? Probably because this thing needs we probably need to write it as A is a type, T is a row tree of T, and this is the thing a row tree of A. Right. So this is now a proof, just as before, but we now have the theorem statement itself in our context. So we have this thing, and this is the thing we're trying to prove. So you might think that it's just as simple as just doing apply rebuild ID prime, and indeed there are no more goals to prove. But when we write QED, it says cannot guess decreasing argument of fixed. Why is that? Let's show the proof. It's built this function which just immediately calls itself. This function doesn't terminate, so Coq doesn't accept it, which is good. But instead we can do we can destruct T. We can do induction of over children. Let's see if we can have auto help us a little bit. Oh, it helps us a lot. No. So here's the problem with this thing. So now auto was again too happy to say, oh, I can just apply this. And for some reason, auto doesn't check if what it's produced is actually, it doesn't check recursion of the thing. So we'll have to do it manually. So here, let's simple, and it's reflexivity. Here, let's simple, and we have, right. So now this thing is a strictly smaller thing than we started with, right? Because this is an element of the children of the tree that we were destructing. So we should be allowed to say rewrite rebuild ID prime to rewrite this thing. And we can do rewrite with our induction hypothesis, rewrite IH children. No. Why not? Oh, I need to simple everywhere, of course. And maybe inversion of IH children. And maybe substitution, no. Simple now. What am I missing? think the inversion isn't this what I have? Found no subterm. Oh, sorry, I'm writing the wrong thing. It's H0. That's why it isn't working. H0. H0. And now this is just reflexivity. So actually, although it helped to build this rose tree induction principle that was more clever about the trees, it didn't. So that allowed us to use the induction tactic with our more clever induction principle. You can also write your proofs as fixed point immediately. The problem is that you have to be careful so that you or the proof search doesn't accidentally produce a proof object that does not terminate. But I didn't know this, and I think writing these things are sometimes a bit tedious. So I think this would have helped me in some cases earlier. So let's start to wrap up. Why don't we? So this is just saying the same things as I did before. Right. So just to wrap up, so I said that sort of programming and logic is the same. If we want to be more specific about it, the Curry-Howard equivalence, sort of the Curry-Howard equivalent of the lambda calculus is intuitionistic logic, also known as constructive logic, and that's logic where rather than saying that something is true or not true, as in false, everything requires evidence. In order to show that something is true, you need to show how to produce that proof. And that excludes some axioms that you have in classical logic. So for example, the law of excluded middle is excluded, double negation elimination is excluded, Peirce's law is excluded, and actually all of these imply the other ones. There are exercises in the book for showing this if you want a challenge. And why is that? So we can actually understand this, sort of why these things are excluded by thinking of our syntactic proofs. So if we have a proof by contradiction that's saying that's trying to say, let's prove P by showing that P not being true is a contradiction. But the problem here is that if we think about it from Koch's perspective, we have not built a procedure for building a proof object for P. We've only built a proof object for not P. No, sorry, we've built the proof object for not P. This should say that this thing leads to a contradiction. However, it's good to know that even though you don't have, for example, the law of excluded middle, you can prove these things you can prove specific instances of these. So for example, we have our is true. We can prove that either something is true or not is true for our little formulas that we had before. We can prove that proof by contradiction works in this particular instance. You can even, and Software Foundations has an exercise for this, you can prove that assuming the law of excluded middle does not lead to a contradiction. You can show that it's okay to assume it, but you cannot prove that it holds. And if you're used to classical logic, this sounds like the same thing, but again, we are interested in computation. We're interested in producing proof objects, producing evidence of something. So it's not enough to show that something cannot not exist. We have to show how you build it. So running just a few minutes over time. So the point of the Curry-Howard correspondence is that it connects logic and program. And Koch is, or most dependently typed languages, I guess, embodies this connection explicitly. So it's not like propositions are like types or proofs are like programs. Propositions are actually types and the proofs are actually programs. We might typically write them using tactics, but as you've seen, sometimes it's useful to program with tactics. For example, when we wrote our special induction principle, sometimes it's useful to prove using program tactics. Again, we wrote an induction principle, and some proofs were quite short. So the thing that you should take from this lecture, other than the Curry-Howard isomorphism being really interesting, really cool, is that proofs and programs being the same thing, it means that we can sometimes switch the glasses that we have on. We can think about things, we can think about proofs in terms of programming, which can be helpful, and we can think about programming in terms of proofs and tactics, and that can also be helpful. And I think I'll wrap up there. Thanks for staying around for the extra 3 minutes.
Great, thank you, Elias. That was a very nice presentation. All right, so just for your information, and the next things coming up is then the guest lecture by Jeremy about that will introduce Agda. So hope that your proof engineering goes well coming weeks. Take care.